Jips, chaps, ladies and gents, good morning. Welcome to week number 10, I think. Yeah, week number 10. You should be in school this week, okay? I think you're coming back on the Thursday, on the Wednesday. But for now, anyway, for this week, we will carry on with the online learning. And we will chat about it on WhatsApp, see what we're going to take it from there when you guys come back. Anyway, we're carrying on with continuity, and for the first lesson this week, and the second lesson, what are we doing the second lesson? We're looking at limits at infinity, which will be quite interesting. The first lesson about continuity is actually, we're not really learning anything new. It just seems like in the first lesson I went a bit over what the textbook already mentioned. So all I'm going to do, I decided I'll do this lesson anyway because it's kind of going to arrange everything we've got so far, which is quite a bit. So we're looking at function, whether they're continuous or not. Okay? So yeah, I think this is going to be quite useful. I'll kind of divide all these classes. So a function might be continuous at, let's say, at specific x, okay, x equal 2, x equal 3, or in this case, we'll just say x equal a. What does it mean that's continuous? If it's continuous, it needs to fulfill three conditions. First of all, the function, the value of the function of at x equal a needs to be defined. Okay? It has to give you a certain value, which is not infinity. What is not defined? For example, if f of x is 1 over x, or let's say 1 over x minus a, then obviously at x equal a minus a is 0, 1 divided by 0 is undefined. So it needs to be defined. Secondly, the limit, okay, we spoke about the limit as x approaches a must exist. That means it doesn't blow up to infinity like here. Okay, obviously there's no limit here when x equal a because it blows up to infinity. But more than that, remember we spoke about the limit approaching. And we can approach a from the right, from greater a's, or we can approach a from the left. And some function, you will get different answers. Like, for example, if you have a split function, okay, and it's split at a, and you have one function for above a, one function below, then you'll have different limits. You have limit for x approaches a from the right or from the left, and they're not necessarily the same. In that case, it's not continuous. And the third condition that must apply for it to be continuous is that the value of the function at a must actually equal to the limit of the function as x approaches a. So just to give you just a simple, let's use the red one, okay? So an example will be f of x equal just anything, x plus 3, okay? X plus 3. If I was to draw that, okay, it's going to be just a straight line crossing the 3. Now I can choose, let's say a equal 2. Let's look at what happens at 2. Okay? You can see that, first of all, f of 2 exists. It's 5. 2 plus 3 is 5. The limit, whether I go from the right to the left, exists, and it's the same. And the value of the limit when x approaches 2, is closer, I get to x equal 2, f of 2 will be closer, f of x, which approaches 2, will be equal to 5. So the limit exists and it's equal to the value of the function. Okay, let's move on to what happens when it's not continuous. Okay, so we looked at two kind of non-continuous function, discontinuity. The first one was a removable function. Okay, it's discontinuous, but it's not that of a big deal. We can fix it. We can remove this discontinuity. So what are the conditions for discontinuity? First of all, the limit, or let's start with 2 actually. F of a is not defined, okay? It's not defined. So I will think about an example like this. F of x equal x squared minus 4 divided by x minus 2. Okay, I think that's kind of the example we had to look. At x equal 2, if a was 2, we can't define f because we're going to have 0 at the denominator. Okay, next thing is that the limit must exist, even though the value, okay, of f at a is not defined, okay. And by the way, sorry, I did say f of a can be defined or not defined. Okay, so there is a possibility that this is it will be defined at a, And I can think about maybe, let me just think about another example. Hang on. Okay, I've got an idea, but I don't want to just introduce it right yet. Okay, so let's just keep it in mind that f of a can be defined or not defined. Here it's not defined, but I'll show you another example where it's defined in a minute. The second thing is the limit, there must be a limit for that function. Whether we approach from the right or from the left, okay, there must be a limit. Okay, so in this case, we said we can rewrite it as x plus 2 times x minus 2 divided by x minus 2. And these things cancel. And then really we can say that f of x is really the same as x plus 2. It's almost the same. The only difference is it's still not defined for x equal 2. Yeah, I know you can put 2 plus 2 here as 4, okay? But that's the limit of the function. It's not the value of the function. You can't put 2 in the x here. Okay? Not allowed. Okay? So what was I? Okay, the limit exists. Whether I come from the right or I come from the left, the limit exists. Okay? Let maybe draw this graph. Can you see if I... Yeah, you can still see. So we said that these two functions are really the same. Okay? So in other words, this function I can just draw as x plus 2. Okay? Straight line going from 2. They're really the same, but they're not exactly the same because at x equal 2, okay, 2 here, we have to remove that. It's not defined. So I need to remove, do a white little circle to show that it's not defined at 2. It is allowed to be not defined. And then, and then the last thing is that the value of the function, okay, at a is not equal to the limit. Now, in this case, this example that I showed you, it's obviously that the value of the function is not equal to the limit. The limit exists. Okay, the limit will be 2 plus 2 will be 4, but f is not defined at a. So obviously, it won't be equal to it. But now, as I promised you, I will show you another example. I'll just pause that for a second. So, example for a function which has a removable continuity, but if they is defined, okay, is one of these crazy functions we spoke about. So I can say it's a split function. So f of x will be equal to x for every x that is not 3. Just try and move it. I don't know if you can see it. I know the light is a bit annoying. I think you can see it. Okay, so if x is not equal 3, then f of x is equal to x. So I will draw straight line. Okay? So the only value where things are defined differently is when x equals 3. So when x is equal 3, then I make f of x actually equal 4. Okay? On purpose. Not 3, 4. So what do I have to do? I have to make a little white circle here at 3 and instead put a little black dot at 4. So we have a little jump. Okay? And that's why we call it, well, it's not a jump discontinuity. It's a removable discontinuity. Okay? So why is it discontinuous? Because the value of f, which is defined here, f is defined at x equal 3. It wasn't defined here at x equal 2, but it is defined at x equal 3. Okay, it is defined, but it's not equal to the limit. Okay? The limit of f of x when x approaches 3, to get as close to 3 as possible without reaching 3, is simply going to be 3, because anywhere else apart from 3, f of x equals x. So it's going to be 3. But f of 3 is actually 4. So it's not continuous. Okay? I'll bring it here, what I said, told you also in last lesson, that a continuous function, okay, is just think about a little man walking on that line of the function. And if he can walk and there's no jumps, there's no gaps, okay, he can just walk. He has tiny little legs and he has tiny little steps, then it's continuous. Okay? If he has gaps or jumps or whatever, then it's not continuous. In this case, right, we have that little gap. Yeah, the poor little fellow will have to go from here up to that little dot and come back here. He has tiny little legs. He can't do it. Okay? But why are we calling it removable continuity? Because it can easily be fixed. How can I fix this function? No problem. Just get rid of that. Okay? And then the black dot will come into here, and then it's continuous. How can I remove this discontinuity? I can just say, okay, so I'm going to say f of x equal that business for everything that x is not equal to. And when x equal 2, then I can just say it is, what was it? 4, I think. Is that right? Because it was x plus 2, so it was 4. And now it's continuous. Okay, now it will have black dot. Okay, last kind of continuity, okay, is called, I'll just say it again, jump discontinuity. And again, jump discontinuity, we have two kind of continuities. Okay? First of all, what's the condition? The condition is, okay, that the limit of the function of x actually doesn't exist. Okay? We don't have a certain value that as we approach x, f of x will get close to. And again, there's really two kind of discontinuities in these jump discontinuity. The first one is a function like this, f of x equal 1 over x. Okay? So if I was to draw that, you can see that one, yeah? If you draw that, then obviously that's hypotenuse. That is a hyperbola, okay? And at x equals 0, okay, the limit of f of x when x approaches 0, okay, there's no infinity, it approaches infinity, okay? This is our next lesson, really, okay? It approaches infinity, blows to infinity, okay? So it definitely doesn't exist. In fact, there is no even limit, okay? Because if I go from the positive side of 0, it goes to infinity. If I go from negative, from the negative side to 0, then it's going to be minus infinity. So there's a huge jump there, okay? In fact, because it doesn't go to any number, it's infinity, really we should be calling these infinity discontinuities or something like that, okay? It's not really jump discontinuity, but in textbook that we're learning, we classify them the same. The second example will be something like this. I think we saw f of x equal x absolute value divided by x. Okay, and I'm not going to go through the whole thing, what's happening there, but we did draw this graph a couple of times, and we know that it looks like that. We've got two straight lines, okay, and before 0 it's minus 1, and after 0 it's plus 1. So there's a jump, okay? So it's not the infinity discontinuity because the values are not infinite here, okay? Right? When I approaches 0 from the right, the limit is 1. It's not infinity, it's 1. But when I approach from the left, it's minus 1. So there's a jump. And that little guy with the tiny little feet, okay? He can't jump from here to here. He definitely can't jump from here to here, but even here he can't jump. Okay? Alright, so continuous or not continuous, removable discontinuity or jump discontinuity. Okay, have fun now with exercise, I think, 4.3. I'll see you now in the next lesson. Limits of infinity.